So let's imagine you have, let's go back to the standard x and y. Let's imagine that my direction L is like this, and it goes through 2 points. Let's say point B, which has coordinate of -4 and 0, and let's imagine it goes through point C, which has coordinate of 0 and minus whatever 3. So that's my direction L, and let's imagine that my vector A is same as before. So I want to do the same thing. I would like to project A along my direction L. Now remember, a vector, as long as you don't change the magnitude and the direction, you can move that vector around. So technically you could move it here. Oops. This is the same vector A which I have translated somewhere on the line L, and what I'm after is the projection of A parallel to L. So I'm looking for this. That's the one I'm looking for. Okay? So again, let's imagine that A has a length of 4 as before. So first we need to express A in component notation. So the x, we recognize a right angle triangle right here. Therefore the x is going to be the cosine. So 4 times cosine 30, which is 2 square root of 3. And then the y is going to be 4 times the sine of 30, which is 1/2, therefore 2j. So same as usual. Now we need to figure out E, which is the unit vector along the direction L. And again, you can pick your E vector either going up or going down. Let's imagine I'm going to pick E going up, and I'm going to plot it from C. And I need to figure out the unit vector E in component notation. For me to be able to do this, the trick is to recognize that the unit vector E is parallel to the position vector CB. The position vector CB is the vector that goes from C to B, which is this vector. So due to the choice of my unit vector E, unit vector E and vector CB are two vectors that are parallel, which makes sense because since E is unit vector of L and CB are on L, of course E has to be parallel to the line going through CB. But specifically, since I choose E to go up, E is not only parallel but also in the same direction as the position vector CB, which is the vector that starts with C and ends at B. So remember the definition of a unit vector. This goes back to the definition of expressing a vector in component notation. If you have any vector, let's say B, you can express B in component notation as bxi plus byj. That's what the book is calling the unit vector notation, and remember, as I mentioned last Tuesday, this is what I call the component notation. The real unit vector notation is this one, where you break down your vector not in component bx and by, but you express the magnitude times its direction, which is expressed by the unit vector. Which means that from this definition, if you solve for E, for any vector, the unit vector is defined as the vector itself divided by its own magnitude. That's how we define unit vector, as you remember from the web lecture. So, in this case, we have realized that E is parallel and is in the same direction as CB. Therefore, E can be expressed and can be calculated as the position vector CB divided by its own magnitude. Now, question. Go for it.
I guess I'm not noticing how it is that you know the angle when you translate vector A to L. How did you know the angles there?
sorry, when I translate my vector A into the black version of A? So this A is being defined as a vector with a 30-degree angle with respect to x, and x is horizontal. So I imagine that I had a little horizontal direction which represents my x, and I estimated that this was roughly 30. So I just translated my vector A and I just placed it anywhere on my line L such that my direction is unchanged and my length is unchanged as well. Does that answer your question? Okay, right on. Yeah, good question. Remember, you can do anything you want with a vector. You can move it around. You can translate it anywhere you want. It's always the same vector as long as you don't change neither its length nor its direction. So you can plot it from the origin of your current system, or you can start it from anywhere. You could translate it towards point B and draw it from point B, or you can move it and translate it to point C and draw A from point C, or from any point on the plane. As long as you don't change neither the magnitude or the direction, those two vectors, this one and this one, are exactly the same vector. Okay, so is everybody with me on my relationship with E and CB based on the definition of a vector expressed in unit vector notation? What I've done is I divided this line by a scalar, which is the length of my vector B. Since in my case E is parallel and in the same direction as my position vector CB, I can express E as the position vector CB divided by its own magnitude. So now next question is, how are we going to express the position vector CB? This is very similar to what you've learned in Math 140 when you calculate the slope of a line going through 2 points. Remember, if you're given, say, a line, and it goes through point A and point B, and this is 2 and 2, and B is 3 and 4, and you want to calculate the slope, you take the difference of the y, 4 minus 2, divided by the difference of the x, 3 minus 2, and you get the slope. The change of y over the change of x. Remember that? To obtain the vector that goes from A to B, we're going to do something very, very similar. Vector AB is composed of the difference of the x and the difference of the y. Since we're going from A to B, we're going to take the difference between B and A. So we're going to take the x component of B, 3, minus the x component of A, 2, and then the y component of B, 4, minus the y component of A, 2. Bang! So this will give us, in this case, I plus 2j. So very similar technique, except instead of taking the ratio of those differences, we're going to take the difference in the x, and that's going to be our I, the difference in the y, and that's going to be our j component. Okay? So, in your particular case, let's obtain the position vector CB. And we need to be very careful, because remember, the position vector CB is the vector that goes from C to B, which is very different from the vector that goes from B to C. Those two are opposite. And that's usually the common mistake that people do when they start playing with position vector. They mix up the direction. So remember, if you're looking for position vector CB, you start at C and you end at B. Therefore, you want to take the component of B, the endpoint, minus the original point, which in this case is C. So what is the x of B? Minus 4. And we will minus the x of C, which is 0. Minus 4 minus 0 is minus 4. And then we'll take the difference of the y component. Again, it's going to be the y of B minus the y of C. 0 minus minus 3, which will give us plus 3. Okay, so now we've just obtained the numerator. The next step is to obtain the denominator. But that's easy. Once we know a vector expressed in component notation, we can easily compute, another hand raised. I'm sorry, go for it. Oh, oh, it was still up since last time. Oh, sorry. Okay. So from this step, it's easy. We can calculate. No problem. We can calculate the length of this vector easily. The length of the vector, position vector CB, is nothing else but, oh, Heath has a nice trick, so I'm assuming it's 5, right? He has that trick 3, 4, 5 triangle. If you don't remember that trick, you can use the brute force. -4, you square it, +3, you square it, you add them up, take the square root. That's 16 plus 6, 25, square root of 25, 5. Excellent. So now we can deduce the exact functional form of our position vector by taking the original vector CB and by dividing it by its own magnitude. And therefore we end up with E equal to -4 divided by 5I plus 3 divided by 5J. And you could check that if you were going to calculate the length or the magnitude of this new vector E, you better get 1. So that's usually a good check to do, because it takes 10 seconds and it will allow you to get the right unit vector before you keep going. Okay, so in this particular case, if you calculate the magnitude, you end up with 16 divided by 25 plus 9 divided by 25. 6 plus 9 is 25 divided by 25 is 1. Square root of 1 is still 1. So we're good. Okay, that's it. Problem is done. So now we need to calculate A dot E. So A dot E times E again will give us, we need to multiply all the x components together. So this times this plus this times this, and we will multiply this result by the E vector again. So we will end up with -8 square root of 3 divided by 5 plus 6 divided by 5, and this number will be multiplied by the unit vector again, which is -4/5 I plus 3/5 J. And this should give us our A parallel. Now let's check. This is obviously bigger than this, therefore this number is negative. This is negative, so the x component is positive and the y component is negative. And sure enough, if you look at this sketch, rough sketch, the x component is indeed positive and the y component is indeed negative. So always check. Whenever you end up with calculating a number, always draw a little sketch and then check the signs. If the signs are correct, then you're confident that you're on the right track. If the signs are incorrect, then you're 100% sure then there is a goof somewhere and you can try to trace it back. Okay? Any questions on this? So again, as I'm doing problems, I will always grab the important theoretical point to remind you what's important. So if at any step of the process you're not sure what I'm talking about and you know that you haven't covered a topic, then write down some notes. Oh, he's talking about this, I haven't seen this, that seems to be important, I need to go back to this. Make yourself a cheat sheet as we go over some problems, so that as you realize that there is some aspect that you're not sure what I'm talking about, it means that you haven't covered yet, so you know you have to go back to this right away. However, if you have covered the subject and I'm doing a problem on this subject and you're still not sure about how I got whatever point or whatever step, make sure you stop me. Okay, raise your hand and then ask the question so we can answer your problem and fix it right away. So, any other questions either on this or on any other part of the assigned homework? Okay, remember how this class is being conducted. I do not teach in this class. I have nothing to teach you. You guys are old enough, you should be able to learn it on your own. What I'm here for is to help you. So I do expect questions. There is no way that everybody mastered everything in chapter 1. So if nobody asks any question, I'm going to move to chapter 2. If nobody asks any question on chapter 2, I'm going to move to chapter 3. because I would assume that if nobody has any questions, that means you mastered material. So it's really your responsibility to tell me, hey, there is some aspect that I don't get it. I like to practice some more. If you don't tell me, I have to assume that everything is fine. Okay, so we have to work together here. Don't let me, run away. Otherwise, if I got no feedback, I'm assuming everything is fine. Okay? Okay, so I got one hand raised and one more problem to do. Go for it, Ed.
Yeah, okay, so on the problem that you got up here, was before you erased that. Um, let's see, we were originally looking for the parallel component of A on L. Okay, so that's going in one direction, and then we arbitrarily chose our unit vector E to be going in the opposite direction of the parallel component of A. And so I'm just trying to sort this out. And you circled some things there at the end where on your last you can where's this thing? Okay. So that's enough. When so you got a negative component here that what is that 8 times negative 8 times the square root of 3 over 5. You got that negative and then negative 4 over 5I there. And that should make a positive. And okay, yeah, no, okay, yeah, there you go. So that's positive, and then okay, so then the y, you've got two positives, yet it should be negative, shouldn't it?
Absolutely, absolutely. The scalar is negative, right? We have minus a square of 3 over 5 plus 6 over 5. So the sum of those two is negative. And the x component of the unit vector is negative. Therefore, negative times negative will give us a positive component. As for the y is positive. Okay, so negative times positive will give us the negative component. Yes, yes, yes. Before I go to number direction check. Yeah. Before we go over 38, there is one more question from Jeremy. The direction check uses the first dot product only, or the final answer. I'm not sure what you mean by direction check. The dot product is a scalar, so he ain't gonna give us... No, that's not the final answer. What you just wrote, Jeremy, is this term, right? Which represents the length of the vector. The final answer, we're looking for a vector, a parallel. Therefore, we need to end up with a vector at the end. So the magnitude of the dot product will tell us something about the length of the vector. If it's positive, then we just take the value as it is. If it's negative, we only consider the absolute value to represent the length of the vector. The negative sign will switch the direction of the unit vector. Okay? Okay, right on. So, I know that it's very odd that we can pick E going up or going down and we end up with the same answer. The answer is because if you pick E in the other direction, the only difference will be the sign. Correct? So E will be multiplied by negative sign. And as we take the dot product, if E is multiplied by -1, the dot product will also be multiplied by -1. And since we multiply the dot product by the unit vector again, then those two external negative signs that just got into our way will be canceling each other. So if you're not... oh, I'm sorry, I missed Lindsay. Let me scroll back up. Yeah, 38. Yeah, I got that. I got that one. 38 is going to be the next step. But before we go to 38, I would like you to be convinced that you can pick E in either direction. And if my answer didn't satisfy you, I would like to redo the exact same problem by picking this time E going down. So let's do this. What's going to be different if I pick E going down? Then this is my E. So what will be different as I calculate E is, since E is parallel to BC, this time I'm not going to choose CB exactly F, I'm going to choose BC. So I'm going to go along BC. And BC is opposite to CB. So BC will be 4i minus 3j. Since the magnitude doesn't change, my new E will be positive 4/5 minus 3/5. Okay, so my E is flipped. There is an angle of 180 degrees. Similar relationship between the resultant vector and the equilibrium vector. The only difference is the direction. So now as I take the dot product between my new E and A, I do the exact same calculation of multiplication. That doesn't change. The only difference between my new dot product and this one is that I will end up with the positive 8 square root of 3 over 5 minus 6 over 5. So it's exactly the same number as I had here, except with a minus sign difference. So now as I multiply my dot product by my unit vector again, the negative sign that shows up here will be cancelling the negative sign that was shown up here again. And therefore, the answer should be no different whatsoever. Okay, so remember, you can always pick in either direction.